Okay, ladies and gentlemen, let's continue with chapter 4, Transient Heat Conduction. In this chapter there are 4 parts. The first part is the lumped system approach. The second one is a transient heat conduction in large plane walls, long cylinders and spheres. The third part is transient heat conduction in semi-infinite solids. And the fourth part is transient heat conduction in multidimensional systems. We didn't finish this part, 4.3. We did finish the theory, but we didn't get to the Heisler charts in detail. We've started with the Heisler charts, but we didn't finish them. And I would also like to do a good example. Okay, so let's just summarize the most important features of the previous lecture. From the one-dimensional heat conduction equation, we ended up with a partial differential equation that could be solved by using the method of separation of variables. But before we did that, we created non-dimensionalized groups so that we can change the 8 independent variables to, let's call it 3 independent variables. And the result of that was that this equation could be solved in a non-dimensionalized format. So this is the non-dimensionalized temperature. Non-dimensionalized temperature is equal to the sum of an infinite series. Okay. And in that we see, ladies and gentlemen, okay, in that we see there's an alpha n and a tau. So that is the non-dimensionalized time. And to get alpha n, we have to get the eigenvalues from this equation. And we have also seen that fortunately, usually the terms become smaller if we work out a problem. There's a similar equation for a cylinder and also for a sphere. In the textbook, it is given in table 4.1. The 3 different equations, plane wall, cylinder and sphere. Take note, for the cylinder and sphere, there are also Bessel functions of the first kind that needs to be solved. And underneath the table, in the fine print, it gives you the non-dimensionalized temperature, the Biot number and the Fourier number. All are defined there. Okay. So those are the equations, and it can be solved by hand, or you can write a computer program. It will take you maybe a half an hour or an hour, and you can write out your own program. But there are 2 special cases. The first special case is to say, well, let's consider a one-term approach. And the one-term approach works well if the non-dimensionalized time is larger than 0.2. Okay, that would give us errors less than 2%, which for most engineering applications are good enough. Okay, so if we now only use the first term, so n equal 1, then we get this equation here. In this equation, this term is also known as A1. Okay, that is A in general. If n is equal to 1, it is equal to A1. If n is equal to 2, then it would be equal to A2, etc. Okay. Now for this, another special case is if we consider if we are interested in the solution where x is equal to 0. Now if we look at the plane wall, then it would be here on the mid-plane. So if we want the solution in the center, there x is equal to 0, and if we put it into that equation, the result is that the non-dimensionalized temperature at the center of a wall is equal to A1 e to the minus lambda 1 squared multiplied by tau. And the authors were so kind to, in table 4.2, to give us the Biot number as a function of lambda and A1 for the 3 different cases of a plane wall, a cylinder and a sphere. There's another approach that we can follow, and that is the so-called graphical approach. And with the graphical approach, it's called the Heisler charts. the Heisler charts. And with Heisler charts, here we've got theta 0. Theta 0. And theta 0 would mean it is equal to the temperature 0. What does that 0 mean? It means where x is equal to 0. So on this coordinate system, x equals 0 would be that point there. So it's on the mid-plane. So theta 0 is equal to T0 minus T infinite divided by the initial temperature minus T infinite. And it is given as a result, as a function of the non-dimensionalized time, tau, which is equal to alpha t divided by L squared. And the results here, the lines are for 1 divided by the Biot number. Okay, now take note that this axis is not a linear axis. It is a logarithmic one. So with some of you doing the practicals, if you go and generate a linear scale, then these are not going to be linear lines, except if you change the one axis to be a logarithmic one. Then you will get linear lines. Okay, so that is the first type of graph which is important to us. The second one is the graph if we would like to get the temperature at any other place. So if we want the temperature there, then that would be equal to theta divided by theta 0. So usually it helps if you first get the center temperature and then you get the temperature at another point. So usually you use, not usually, in many cases you're going to use this graph first to get the center temperature, then you use this graph to get the temperature at any other point. So that would be equal to T minus T infinite divided by T0, Ti minus T infinite. And this is now given as a function of 1 divided by the Biot number for different lines of x divided by L. Okay, so that is the second Heisler chart. And the third one gives us the heat transfer. So Q divided by Q max, and that is given for the Biot number square multiplied by tau for different values of the Biot number. Okay. Now one of these sets of graphs would be valid for the plane wall. On the next page, there's one for the cylinders, and the third one is for the spheres. So depending on the geometry, you're going to use the correct Heisler chart. Okay, so that is the theory part of paragraph 4.3. Before we go on to a problem, any questions on the theory? Nothing, okay. In terms of a problem, let's consider the previous problem that we've considered with the lumped system approach, and that is the dead body. Okay, the dead body that was discovered, at 1700 hours. And when the temperature of this body was measured, it was 25 degrees Celsius. Okay. And it was in a room where the temperature was 20 degrees Celsius and the heat transfer coefficient was 8 watts per square meter degree Celsius. And we have assumed that this body can be approximated as a cylinder with a diameter of 300 millimeters and a length of 1.7 meters, 1,700 millimeters. Okay. Now, let's first solve the problem using the lumped system approach. The lumped system approach. So the question was, The question was, when did the person die? Okay, so that was the question. And to answer that, we also know that the initial temperature of the body must have been 37 degrees Celsius, okay, before the person died. In terms of the lump system approach, we've said that let's start by calculating the characteristic length. And the characteristic length would be equal to the volume divided by the surface area. Okay. And the volume is equal to pi divided by 4 multiplied by the diameter squared divided by the length. And the surface area would be this surface area on the outside of the cylinder, which is equal to pi multiplied by the diameter multiplied by the length, plus the surface area here, this one here, plus the one here on the back, which means it is 2 times that one, plus 2 times pi divided by 4 d squared. And we've calculated it previously as 0.0689 meters. The Biot number is a function of the characteristic length. It's equal to the heat transfer coefficient multiplied by the length divided by the thermal conductivity. The heat transfer coefficient is equal to 8. The characteristic length is equal to 0.0689 divided by the thermal conductivity, which is equal to 0.617. In terms of the properties, we've said that we would consider the properties at the average between the initial temperature and the temperature at which the body was discovered. So that is at 31 degrees Celsius. So at 31 degrees Celsius in table A9, the properties of water are given. And the properties for water at 31 degrees Celsius are K, which is equal to 0.617, the density, which is equal to 996. I'm not going to write down the units now. Cp is equal to 4178. And alpha, which is equal to K divided by rho Cp, is equal to 1.4827 e to the minus 7. Okay. K is equal to 0.617, the thermal conductivity. The density is 996. Cp is 4178. Alpha is equal to K divided by rho Cp is equal to 1.4827 e to the minus 7. So from this we can calculate the Biot number as 0.89. Okay. Which is not smaller than 0.1. Which means that it is going to give us an approximation. At best, it's going to give us an approximation. Okay. And then we've used this to calculate the temperature T minus T infinite divided by Ti minus T infinite, which is the non-dimensionalized temperature, is equal to E minus BT, and B can be written as the heat transfer coefficient multiplied by the surface area multiplied by T, rho, the specific volume, and Cp. We can say that here we've got the volume divided by the area, so we can write it in terms of the characteristic length. So it is e to the minus ht divided by rho, Lc, and Cp. Okay, the temperature when the body was discovered is 25. The temperature at time equal T is 25. The room temperature is 20. The initial temperature of the body before he died must have been 37, and the room temperature is 20. It's equal to e to the minus, the heat transfer coefficient is 8, multiplied by T, divided by the density. The density is 996. The characteristic length is equal to 0.0689, multiplied by Cp, which is 4178. The only unknown is the temperature. So the temperature T is equal to 43,860 seconds, which is about 12.2 hours, and that would mean the time of death should be at approximately 5 o'clock in the morning. Okay, do you remember that? Okay. Okay, now we've got the tools. Now we've got the tools to actually get a better answer. Because now we can say, well, we've got a cylinder, we've got the solution for a cylinder, so let's use that. Okay? So, in terms of a cylinder, the length of the cylinder divided by the radius, the length is 1,700 and the radius is 0.15, which means the ratio is larger than 10. Therefore, the long cylinder approach would give us a good answer. Okay. Now from table 4.2, the Biot number is equal to 0.89. Now there is a line for 0.9. So without doing interpolation, just because I want to show you the principle, we can get alpha 1 is equal to 1.2048 and A1 is equal to 1.1902. Do you agree? If you look at those values. Okay. Therefore, we can say the non-dimensionalized temperature 0, what does it mean? It means for at the center. For a cylinder is equal to T0, it means at the center, T0 minus T infinite divided by Ti minus T infinite is equal to A1 e to the minus lambda 1 square multiplied by tau. temperature at the center, and now we have to make an assumption. Let's suppose the temperature was measured with a thermometer at the center of the body, 25. Okay. So it means everywhere here on the center, the temperature should be 25. 25 minus 20 divided by the initial temperature is 37. The room temperature is 20 is equal to A1, which is equal to 1.1902 e to the minus 1.2048 square multiplied by tau. Are you happy with that? There's nobody here that's not happy with what I've done. Ladies and gentlemen, it's all wrong. There was a catch. It's all wrong. You were asleep. What was the problem? And I've warned you that when we did the lumped system approach. When we did the lumped system approach, I said that in the calculation of the Biot number, we use a characteristic length. But for other cases, you do not calculate the Biot number like this. You remember? Okay. So let's go and do it the right way. The right way is to say, if we look at table 4.1, in table 4.1, it says in the fine print, the Biot number for a cylinder is equal to the heat transfer coefficient multiplied by the radius divided by the thermal conductivity K. The heat transfer coefficient is equal to 8. The diameter is equal to 150 millimeters, so it is equal to 0.150 divided by the thermal conductivity, which is equal to 0.617. So the result of that is that the Biot number is equal to 1.944, and that is going to give you other values for lambda and A1. Okay, so for a Biot number of 1.944, or I'm going to use the value of 2 so that I don't need to do interpolation. Okay. Lambda 1 is equal to 1.5995, and A1 is equal to 1.3384. So in that for that same equation, theta, the center for a cylinder, is equal to the temperature at the center minus T infinite. The initial temperature minus T infinite is equal to A1 e to the minus lambda 1 square multiplied by tau. The center temperature is 25. The room temperature is 20. The initial temperature before the body died must have been at 37 degrees Celsius, and the room temperature is 20, is equal to A1, and A1 is equal to 1.3384 multiplied by e to the minus lambda 1.5995 square multiplied by tau. From where you can solve that tau is equal to 0.5 5923, the non-dimensionalized time, which is equal to, and again, there it is. I mean, you don't need to remember it. It's equal to alpha t divided by R0. Sorry, R0 square. Okay. From where we can solve that the time must be 89,881 seconds, and that is 24.96 hours ago. So it's almost 25 hours. So the time of death is the previous day at 1600 hours. Remember, the body was found at 1700 hours, so it's 25 hours before that, so it's the previous day at 1600 hours.
So do you expect us to interpolate the table straight test example, or do we just round to the
question is, do I expect of you to do interpolation during the tests and the exams? The answer is, listen well, listen. The answer is, in engineering there are not always these types of rules that you should do that and you shouldn't do that. You should use your discretion. And what I mean with that is, if you look at the table in terms of the Biot numbers, sometimes you have to decide if they are too far apart. Okay. If the values are too far apart, then you have to use your discretion, and maybe you will have to do interpolation. But in the test and exams, for me, it's about the principles. So yes, then you don't have to do interpolation, except for those special cases where you have to use the discretion and it's too far apart. Okay. Okay. So ladies and gentlemen, that is the first method of solving this problem. We can also use the Heisler charts. So let's use the Heisler chart. Okay, the Heisler charts. Okay. The Heisler chart, the first chart, gives theta 0 is equal to T0 minus T infinite divided by Ti minus T infinite. Okay. The temperature at the center is 25. The room temperature is 20. The initial temperature 37. The room temperature is 20. That would mean at 0.294. Okay. Now, if you go and look at this graph, there's no way that you can go and read off a value of 0.294. Okay. I've tried my best, and I could only settle on 0.3. On 0.3. Okay. Then we've got the lines of 1 divided by the Biot number, and that would be equal to 0.514. Okay. So if we take this Biot number, 1 divided by 1.944 is equal to 0.514, and I could only manage the line of 0.5. Okay. So for the line of 1 divided by the Biot number is equal to 0.5, you can read off the value of tau. I could read off a value of 0.6, okay, which means that tau is equal to alpha t divided by R0 square. The non-dimensionalized time is equal to 0.6. Alpha is equal to 1.4827 e to the minus 7 multiplied by t. divided by 0.15 square, from which we can solve the time as 91,050 seconds, and that is 25.3 hours ago. Okay, so if we compare it, we can see it is quite close, but obviously it is not that close. So the graphical method doesn't always give that good answers. It depends on the resolution and where on the graph you are. Okay, any questions on the problem or this part of the work, paragraph 4.3? Okay, if not, ladies and gentlemen, thank you very much. Okay.